Okay, so now, yeah, we're going to look at a bit more than this, but mostly we're going to look at how CO2, basically the interactions between climate and the oceans, and how the ocean affects CO2 and in the climate system. So we'll be looking at the ocean carbon pumps, which Pete already talked about a little bit yesterday. And then we'll be looking at how climate might change the performance of these pumps. And I'll introduce something called the Ravel buffer factor, and probably will run out of time, unfortunately, because it's the most interesting thing. But we'll also touch on glacial, interglacial changes in CO2 and how the ocean's role in those changes. So this is a depth profile, kind of an average depth profile of DIC and alkalinity in the oceans. It's not that important, but the black ones have been normalized to salinity to just remove the impacts of precipitation and evaporation or variations in salinity from place to place. But you can see there's a strong, like we saw in the profile, in the sections, there's a strong depth gradient in DIC, where it's much lower in surface waters and it increases in deep waters. And there's also a bit of a depth gradient here in alkalinity, although it's much less pronounced than for DIC. So these, the fact that there's low concentrations in the surface waters and deep concentrations, high concentrations in deep waters, even though the ocean circulation is always trying to homogenize these concentrations, we say that there's some pumps operating. Carbon pumps are operating to maintain this gradient in DIC and alkalinity between the surface and the deep ocean, because the mixing is always trying to homogenize these fields. So there's really two pumps that are performing this, maintaining this gradient. One is what Pete talked about yesterday, which is a biological pump, and the other one is what we call the solubility pump. So the biological pump is summarized here in this pretty picture, which is just the fact that carbon fixation or photosynthesis is taking up carbon from the surface waters, and then they're sinking out of the surface waters into the deep sea and being remineralized and increasing the DIC in the deep water. So that's called the biological pump. There's also this calcification pump that's shown over here, which is slightly different. So here we have, this is sort of a net reaction of calcification, and that's also bringing some carbon to the deep sea. But the other thing that it's doing is, and it's contributing to the distribution in alkalinity. The other thing that calcification does, though, is that it actually, because when you remove alkalinity, you increase the PCO2. Remember, there was that inverse relationship between alkalinity and PCO2. So calcification actually increases the PCO2. So when there's calcification, the net reaction is actually to cause a flux of CO2 from the ocean to the atmosphere. That's why there's a positive arrow here. So calcifying organisms are kind of unique in that they actually they cause CO2 to go into the atmosphere. So if you're an oyster farmer and you're growing a lot of oysters, actually not increasing carbon removal from the ocean, you're actually contributing to carbon efflux from the ocean into the atmosphere. So it's an important distinction to be made about calcifying organisms. Now, obviously, the ratio between, and this is something we'll look at in the lab this afternoon, the ratio between the calcium-producing organisms and all the, well, here it's showing some calcium organisms. So the ratio between the organisms that produce calcium carbonate and those that don't, that ratio, like the calcium carbonate to organic carbon production ratio, so the ratio between phytoplankton that make carbonate shells and those that don't, that's actually an important variable that determines the alkalinity balance of the ocean and can have an impact on atmospheric CO2 sort of through this process. So yeah, that's the biological pump. And then the other one is what we call the physical ocean carbon pump, the physical ocean pump, which is the fact that cold waters are, gases are more soluble in cold water. So the CO2, the cold waters can hold more CO2 than the warm waters. And the cold waters are, the cold waters, the waters that then become dense enough to form deep waters. So we have cold waters holding a lot of CO2, and then they fill up the deep ocean. with their cold, dense waters. And so this process of just cold, carbon-rich water sinking into the deep sea and then upwelling into the surface, warming and letting off CO2, that's another pump. Basically, the fact that the deep ocean is cold is another reason that the deep ocean has high CO2 concentrations. So these are two processes that are occurring. And we can ask, like, which pump is actually more important. And these graphs give us some idea as to that. So we talked about the Redfield ratio before, which was the ratio between carbon, nitrogen, and phosphorus in phytoplankton cells. So if we look at just the global distribution of phosphate and DIC in the oceans, we can see that there's a pretty good correlation between those two parameters. And so that's saying that a lot of the variability that we see in DIC is related to phosphorus, which is a nutrient, and that the slope of that line, well, that's not the slope of the line, but this 117 to 1 is sort of what we would expect from, it's kind of the Redfield ratio that we would expect to see if all of the, just based on remineralization of typical organic matter. And the data kind of fall very close to that line. So that's telling us that the biological pump is quite important in determining the distribution of DIC that we see in the oceans. It's not completely perfect, obviously. If it was just biology, all the points would lie exactly on this line, but it seems to be explaining a lot of the variability. A lot of the gradient in DIC appears to be accounted for by the biological pump. Now, but the temperature also seems to be important. So if we look at DIC as a function of temperature, this line here, so this is DIC, not PCO2, but we could actually calculate the temperature sensitivity if we assume that the ocean is in equilibrium with the atmosphere at a certain temperature. So DIC doesn't actually, depend on temperature in sort of a thermodynamic sense, but we could imagine equilibrating the atmosphere with different temperatures of water and then going through the whole inorganic carbon system. So if we did that, we can get kind of a theoretical line of how much DIC we would expect for change in temperature, and that follows this line here. And you can see that the data kind of fall along that line as well. So from these two plots, we can sort of just qualitatively say that it looks like the biological pump and the solubility pump are both important. They're both playing a role in determining this gradient in DIC between the surface and the deep water. Now, more in the textbook, they go through a more sophisticated analysis of this and determine that the biological pump is, I think, something like 70% of the variability or something, and the solubility pump explains the rest of it. But basically, both of the processes are important in maintaining that gradient. I'm not sure what I was going to say about this. I just wanted to, well, we'll see this in the lab. I just wanted to reiterate that we see these vertical differences in carbon, and that those are actually, when in the lab, we'll look at the North Atlantic and the North Pacific, and you'll see differences in the North Atlantic and the North Pacific that reflect the fact that the North Atlantic deep waters are much younger than the North Pacific deep waters. So basically, they have less decay products in them than the North Pacific. So the North Pacific ends up looking more kind of like a super deep water. It looks like deeper water than the North Atlantic. It's looking more, has more accumulation of the decay products. Don't think I need to talk about this one again. Okay, so those are the carbon pumps. So then we can ask, so that's how they're, oh yeah, this is what I wanted to say. So this graph, again, was the surface PCO2 and was showing the exchange of carbon between the ocean and the atmosphere and the fact that the ocean is taking up carbon from the atmosphere right now. And that's thanks mostly actually to the solubility pump. And so it's really important to know, like, how are these pumps going to change in the future? Is the ocean going to keep taking up this much CO2? Is it going to suddenly start taking up more CO2? Is it going to take up less CO2? So we need to have a think about how these pumps are going to operate in the future. So, like, if the pumps are becoming less efficient as temperature changes and the climate changes, then that means that more CO2 is going to end up in the atmosphere. That would be a positive feedback. And if the pumps are for some reason less effective in the future, then that would be a negative feedback. More effective in the future, that would be a negative feedback. More CO2 will end up in the ocean and less would accumulate in the atmosphere. So we need to have a think about what will control the efficiency of these pumps. So in terms of the biological pump, the biological pump, the efficiency of that pump depends on the supply of limiting nutrients. Not so much the supply, a lot of the nutrients like nitrogen is supplied by upwelling from deep waters. But when you have upwelling, that's also supplying carbon. So you can kind of think of the biological pump as the net removal of nutrients, the balance between the upwelling and the biological removal. So say if you have, so we're really looking at kind of the input of nutrients external to the system, because the nutrients that are coming in from upwelling, they're also kind of carrying carbon with them, so they're not really helping, if you know what I mean. So if you had like runoff of nutrients from land, that's like an extra source of nutrients that could then allow carbon to be taken up beyond what it could take up if those external nutrients weren't added. If you had in the iron-limited Southern Ocean, where the nutrient uptake isn't 100% efficient today, if you dumped in a bunch of iron there, then you would relieve those phytoplankton of their nutrient limitation, their iron limitation. Then they could suck up all that nitrate that was kind of hanging around, and that would make the biological pump there more efficient. So in terms of what's going to happen into the future, well, actually, we really have no idea. There's different models of how dust input to the ocean is going to change, and the last time I checked, like some of them said it was going to be higher, and some of them said it was going to be lower. So we really don't know. There could be increase of nutrients from land due to sort of human influences, but that's probably going to be limited to sort of coastal areas. Might not have a global impact. Sunlight is really important in determining the impact of the efficiency of the biological pump. Probably not going to change, but maybe cloudiness would change. Hard to tell. There was a lot of interest in UV damage because of the ozone hole, and that would, if you really zapped phytoplankton and disabled them, that would obviously negatively impact the biological pump. There's some effects on the food web. So we've only been talking about phytoplankton, but if you increase the sort of the levels, the number of trophic levels in the food web, you could increase the amount of respiration that's happening and sort of decrease the efficiency of the transfer of carbon from the surface ocean to the deep ocean. So there are some effects, and this has hardly been studied at all. It's possible that food webs will change in the future, and that could change the efficiency of the biological pump. And then ocean acidification, again, this has not really been studied in any great detail. The net effect of ocean acidification on the biological pump is, again, a big unknown. So I'd say, sadly, we actually have very little idea of how the biological pump is going to change in the future. But there's a lot of interest in trying to understand that, obviously. In terms of the physical pump, we have a better handle on these variables and how they might change. So surface temperatures, particularly in the areas where deep waters have formed, that's going to be really important in determining how much carbon is taken up by the ocean through this physical pump. And like I showed in the previous slide, so warm water holds less CO2, and the solubility of CO2 is greater in cold water. And we know that the surface temperatures are going to increase. So that means that in those areas, the ocean will be able to take up less CO2. So the warming is going to directly decrease the solubility pump, because the oceans will be able to take up less CO2 because it'll be warmer. And we also have, as oceans get warmer, as the surface of the ocean gets warmer, those waters get lighter and the ocean becomes sort of more stratified, and the deep waters just aren't going to form as much because they're not as cold and not as dense. So if the deep waters aren't formed, then that CO2 isn't going to be sort of delivered into the deep sea, so that could decrease the solubility pump. Another variable is actually the concentration of carbonate ion that the CO2 is going to react with. So as the CO2 goes into the seawater and reacts with that carbonate ion, Eventually, there's sort of a finite amount of carbonate ion in the seawater, and eventually it'll be kind of all used up, and then that will decrease the ability of the ocean to hold CO2. But that's going to happen kind of on long time scales. So this brings me to this buffer capacity idea, which is summarized by this Ravel factor named after the guy who coined the term. So basically, as the Ravel factor tells you how much, it's this ratio here, it's for a given change in DIC, so as the ocean takes up carbon and increases its DIC, the relative change in CO2 that you get for a change in DIC. So as you put CO2 into the ocean, it doesn't all become, you don't get a proportional change in PCO2. Some of it is sort of buffered by this carbonate ion, and you can get kind of a large change in DIC and not much change in CO2 if you have a lot of buffering capacity, a lot of carbonate ion. But the thing is that capacity is limited, and it varies today in the ocean according to this map here. And also, as you add more CO2 into the system, you use up the carbonate ion, and you end up getting a proportional larger change in CO2 as you pump carbon into the ocean. So that's what's shown here. As you increase the PCO2, the buffer factor increases, and that means that in the future, as you add more CO2, you're going to get proportionally more change in PCO2, which really means that the ocean isn't going to be able to hold as much CO2 because more of it's going to be in the gas, and it's going to want to kind of get out into the atmosphere. So higher values of this number mean the ocean isn't able to hold as much CO2. Now, in the distribution of the Ravel factor in the ocean today looks something like this, where you see actually quite high values of the Ravel factor in the Southern Ocean, and that's really because of upwelling of deep water. It has very low carbonate ion because the deep waters have low carbonate ion. There's a lot of upwelling in the Southern Ocean, so these waters have low carbonate ion and therefore a high Ravel factor. So high Ravel factor means low ability to take up CO2. Today it's mostly related to the carbonate ion content of the water, but then as we go into the future and the ocean's absorbing more and more CO2, it's going to sort of burn up that carbonate ion that's there, and it's going to be less able to take up more CO2. So I've been mostly talking about equilibrium, but then the kinetics of all this is quite important, and in this paper they estimated that so over about several thousand years, about 90% of the CO2 emissions, of anthropogenic CO2 emissions, will end up in the oceans. But because the oceans are mixing, like the time scale of mixing of the oceans is a limiting factor here. So right now, the oceans have only taken up about 1/3 of the amount that they sort of theoretically could take up if it wasn't limited by this mixing, the mixing of the oceans. So currently, the uptake it's not really just driven by the chemistry, it's also driven by the dynamics of the ocean circulation. Which is just shown here, but I'm going to skip over that. Okay, so Pete showed a graph like this yesterday. So this is a graph showing how carbon dioxide in the atmosphere has changed over time from the Vostok ice core. Showing from 400,000 years ago to today. And so these are reconstructed from bubbles from ice cores, so we can go back in time and look at how the atmosphere changed through time. Then here are some modern measurements from Hawaii showing how CO2 is changing today. So this is the anthropogenic signal here. And here it is drawn kind of on the same scale as the Vostok ice core. So we see that and these are, obviously there's no fossil fuel emissions going on back here. These are just completely natural variations that are occurring through the Earth system. But you can see that the changes that occurred in the past were really quite large. And they're in fact just as large, although over much longer time scales. They're the same magnitude, the same size as the anthropogenic perturbation. But like I said, obviously the rate of change is enormously faster in the anthropogenic case. And if we look, there's this really consistent cyclical pattern in the variations in CO2. And so a big question driving a lot of research in sort of the carbon system is to understand what natural processes were driving these massive changes in carbon in Earth's atmosphere in the past. And we know because the ocean holds, like I said, 60 times more carbon than the atmosphere, and it can exchange quite quickly, we're pretty confident that these changes were driven by changes in the ocean. This is just similar to what Pete was showing yesterday. These are the CO2 variations that were from the previous slide, and here's the temperature reconstructed from the ice core. So just showing that these changes in CO2 were occurring in concert with what we call the ice ages of the Pleistocene. So during the warm periods, we have high CO2. During the cold periods, you have low CO2, and so on, going back in time. And it's been estimated that the changes in CO2 are actually responsible for about half of the change in temperature. So the changes in CO2 are directly contributing to the kind of the size of the ice ages, the size of the climate change that occurred because of the radiative forcing associated with the CO2. So these are just the ice sheets. This is the not very much ice, lots of ice, and so on. These are the ice age cycles going back in time. That's what I said. So it's amplifying what we call the orbital forcing. Now, if we go back to the the global carbon cycle, so obviously during glacial times, this number was a lot lower, and we can ask, well, what was it about the Earth's carbon system that was different, that changed, which one of these arrows, ignore the red arrows because the red arrows were not happening back then, which one of these black arrows changed, which box here changed its size so that basically some of these boxes down here must have had more carbon in them because there was less carbon in the atmosphere. So I already told you that we are highly suspicious of this ocean pool because it has so much carbon in it. It has big leverage on the atmospheric CO2. So so attention has been paid to what was the ocean's role in driving these changes in CO2. The ocean was clearly holding a lot more CO2 during glacial times, taking it out of the atmosphere. So the CO2 during glacial times is about 80 to 100 parts per million lower than during interglacial times. And there's a few obvious explanations that we can go through. So one is that the terrestrial biosphere was reduced during glacial times. So we had all these plants here would have been covered in ice sheets. There were big ice sheets during glacial times. Probably would have vastly reduced the uptake of carbon by the terrestrial biosphere. And in fact, if we look at the carbon isotopes in those ice core records, we can see evidence that that was the case. So we can kind of estimate how much less abundant the terrestrial biosphere was using carbon isotopes. And we come up with, since the terrestrial biosphere was wiped out, there was probably about 15 parts per million more CO2 that just went into the atmosphere because that terrestrial biosphere box was reduced. So that's not helping us. It's actually making the problem worse. The surface ocean was colder because it was a glacial climate. And so that's going to be increasing the solubility pump because the ocean's able to take up more CO2 because it's colder. And we can calculate that that would have lowered atmospheric CO2 by about 30 parts per million, just based on the temperature. And then the salinity would have also increased, though, because you have all this water that was now in ice sheets that would have actually kind of concentrated the remaining salts. That would have increased the salinity a little bit. And that would have decreased the solubility because of the effect of salinity on solubility. So that's going to increase the CO2 a little bit here. So if we add all these things together, here, we get a total CO2 change of minus 8.5. So it's really not very much. Haven't gone very far in explaining our 80 parts per million decrease in atmospheric CO2 based on these sort of obvious changes. So that means we need to invoke changes in the probably in the biological pump or the solubility pump, more sort of fundamental changes in the way these pools were operating. Now, this has been a question that's been received a lot of research attention over the past 25 years or so. And so this is a table from the textbook of just like a small sample of the many, many, many hypotheses that have been put forward to explain this, this puzzle. So there's really no shortage of hypotheses to explain the low glacial CO2. And I'm not going to go through all of them. And I'm just going to sort of focus on a few that relate to biogeochemistry, because that's what we're talking about here. But you can have a look here. So there's, there's a lot of, there's some hypotheses that, there's a lot of focus on the Southern Ocean, because if you look at, well, if you look at the temperature graph that I showed before and the CO2 graph, that temperature was from Antarctica. It was from an Antarctic ice core. And if you look in detail at the temperature changes and the CO2 changes, they're very, very closely matched. So that it seems like the CO2 responds really closely, follows the changes in temperature in Antarctica very, very closely. And in fact, a few years ago, there was the Antarctic ice core record was extended many hundreds of thousand years, and there was a contest at the AGU meeting for modelers to predict what the CO2, they had measured the temperature, and they were asking the modelers to predict what the CO2 was. And there was like a little contest, and there were some posters, and the group that got it correct, all they did was basically a linear regression between the CO2 and temperature from the previous records, and they just extended that back in time, and it matched the best. Like, it was much better than complex biogeochemical models. Was just this empirical relationship between the Antarctic temperature and CO2. So there have been a lot of, and also because of the high latitude dominance that I talked about before, a lot of hypotheses focusing on the Southern Ocean. And here's some. And then you notice they all have problems. Most of them have problems with them. There are other hypotheses that are relating to areas of the ocean outside of the Southern Ocean driven by physical changes. Oh, so here we've got, you could cover it with sea ice. You could change deep ocean stratification. You could fertilize the ocean. Then you could change things to the low latitude waters. Then you can change the biological pump outside the Southern Ocean. You can change the carbonate pump. So there's a lot of different hypotheses, and if you put them all into a model, it's very, very easy to account for the full magnitude of the change. It's just that they all have sort of problems with matching up with observations, and the observations have problems. So it's actually not clear at all what really happened. So just to give you a sense of, and we'll look at this in more detail this afternoon, but this is results from a simple two-box model, just to give you a sort of sense of how sensitive the atmospheric CO2 is to changes in these pumps. So this is a result of a two-box model, similar to what I showed in the second lecture, I think, where we're going to change the solubility pump and the biological pump. So if you just take the standard ocean with a average temperature of 20 degrees and a phosphate of 0.5 micromolar, you can end up with this nice atmospheric CO2 that's about what it is today. And if all you do is cool that ocean by 5 degrees, you can draw down the CO2 to about 304. And if you warm it up, the CO2 in the atmosphere goes way up. Then you can also mess around with the biological pump, keep the temperature the same. And here we're just going to kill all the biology in the ocean. So the deep ocean phosphate the surface ocean phosphate is now the same as the deep ocean because there's no biology removing it. And that obviously has just an enormous impact on atmospheric CO2. So now we've just shut down the biological pump, and all that CO2 that was being removed by the biology has now gone into the atmosphere. It has a huge impact. So thank the biology, otherwise it would be very hot here. If we then take all the phosphate that was there, so here we just had half a micromolar. That's kind of an inefficiency in the pump because there's some phosphate left. If we allow the biology to suck all that up, we're able to reduce the atmospheric CO2 down to sort of almost glacial levels. So these pumps can have quite a big impact on atmospheric CO2. Obviously, this is a very, very simplistic model, but just to give you an idea. And you can play with the three-box model some more this afternoon. So one thing that was realized quite early on in this is that the two-box model is kind of limited in explaining the dynamics of the carbon system. And a bunch of groups in 1984 simultaneously hit upon this idea of the importance of the high latitudes. And the idea that it's actually not all surface waters are created equally. It's actually these high latitude ocean has a disproportionate impact on atmospheric CO2. And there were these three groups from Harvard, Princeton, and Switzerland. And so they were kind of nicknamed the Harvardton Bears because of where they came from. And they came up with this idea of the fact that there's a connection between the high latitude ocean and the deep ocean due to the fact that the deep waters are formed in the high latitudes. And this thing called isopycnal ventilation, which I realize I should probably, I'm not a physical oceanographer, so I'm going to do a very primitive picture of what circulation looks like in the ocean. But say we had, say this is the Southern Ocean here, and this is the equator. And this is the surface ocean, and this is like deep. What happens in the Southern Ocean is there's, well, there's some winds blowing, the westerly winds, and they're causing, they're kind of, basically there's this transport of water away over here, and you can kind of think of the winds as like pulling up the deep ocean up to the surface. So you have these density layers that are in the Southern Ocean. They basically have the deep water that's sort of deep is at the surface in the Southern Ocean. We call this upwelling. So there's sort of, it's like the deep waters are at the surface in the Southern Ocean because of the way the circulation is kind of sucking up these waters in the Southern Ocean. So this is a very primitive picture of what the circulation looks like, but essentially what you have is a connection between the high latitude surface ocean and the deep ocean. And these groups determined that was really important in determining atmospheric CO2, that the high latitudes had this disproportionate impact. Let's get rid of my ugly drawing. And so, one other thing I want to mention here. So the model that we're going to be looking at this afternoon is a 3-box model. It's actually, and I included a paper by, well, it's a paper by Togweiler. It's not this paper, but it's a paper that describes the model in a lot more detail. So if you're interested, you can have a look at that. But these other two models are very similar. So yeah, they came up with this 3-box model idea where you have a high latitude box that is communicating quite closely with the deep ocean, which is supposed to simulate that upwelling that I was talking about. And that the high latitude box has sort of different biological properties than the low latitude box, that you have nutrients up here that are not being completely used because the biology is inefficient for some reason. So there's sort of chemical and physical differences between the two boxes. Not sure why I showed that. So this is just what it looks like more formally. Okay, so this graph here is showing kind of the importance or how this works in terms of CO2. So, and here we've introduced the idea of a window. So we can think of the high latitude as kind of being, the high latitude box as being a window for CO2, that we can either have the window be open and all the CO2 from the deep sea is going to go into the atmosphere, or we can have that window be closed and we're going to kind of minimize the release of CO2 from the deep ocean into the atmosphere. So you can imagine these cases here. So here we have the pre-industrial case where you have the phosphate in the deep ocean. We have the low latitude surface box where the biology is very efficient. It's removed all the phosphate. And then we have the high latitude box where there's quite a bit of phosphate being left over that's not being used by the biology. And if we let that come to equilibrium, we get sort of nice atmospheric PCO2 of 280. Now, if we crank up the biology in the high latitude box and sort of close that window, so now say we've sprinkled some iron into this high latitude box and the phytoplankton are now happy and they're able to use all the phosphate that's there, so they suck that down to 0. That has a big impact on the atmospheric CO2 and it's now decreased it to 160. here, if we open up the window completely, we let the high latitude box basically be exactly the same as the deep ocean. Now the biology is completely inefficient in the Southern Ocean or the high latitudes, then that increases the atmospheric CO2 to 425. So this is kind of the same, and this equation down here is explaining how the DIC in the high latitude box is a function of the rain of organic matter from the high latitudes, and that the flux term and the exchange rate between the high latitude box and the deep ocean. So really, if we can think of this sort of window, there's kind of two main ways that we can close the window for the high latitudes. One is to increase the stratification. Another way of thinking of that is to decrease the exchange between the deep ocean and the surface box. So that's this this term here. If we kind of decrease that exchange rate, we'll just decrease the rate at which the CO2 from the deep ocean is getting into that high latitude box. And so that will kind of seal off the surface ocean from the deep ocean and allow less of the CO2 to get to the atmosphere. So if we just change the physical exchange rate, that's one way of closing that window. So that's by decreasing this number here. Another way of closing the window is to increase